So, hello everyone. My name is Dixon Wong, and I'm a postdoctoral visitor from the York University, which is Canada. So today I'm very happy to deliver a talk on the topic about the modular bio-inspired soft robot designs for adaptive locomotions and manipulations. So in this talk, I will introduce three of my past projects, and actually, all of them are actually based on bio-inspiration. Okay, so let's go for the first one. So the first one actually, the title is that the design of the reconfigurable and transformable soft pneumatic actuators. Actually, it is inspired by the human hands. So as you can see in the figure, so for the human hand, it is very easy for us to do the adduction, and also flexion extension. However, it is not that easy for a finger to do the twisting motion because of the biological structures of the human bones. And then up to now, actually, there are a lot of research based on the bio-inspiration of the human fingers, and then they've developed different kind of the soft actuators which can do the bending or twisting actuations. However, actually, right now it seems that, to my knowledge, actually there is no actuator which can do the both actuation, which can do the bending and twisting at the same time. So that's why I proposed the design of the so-called RTSPA in the short form. So as shown in the animation here, so you can see that in this new design actuator, it can do both the tunable bending, adduction, and also twisting motion in only one single actuators. And also, the other important point is that I only require to use only one single pneumatic controls to control the motions of these actuators. Okay, so we can see that from the figure here, you can see that there are two main structures of the actuators, so-called the rigid rotation mechanism, the RRM, and also the soft actuation mechanism, the SAM. So here is the details of the design of the rigid rotation mechanism. So as you can see from the name, actually it is a rigid structure which is made by 3D print by PLA. Okay, so the main function is that it is used to change the posture of the actuator so that it can achieve different tunable bending and twisting action. So you can see that by different configuration, you can see that I have two motors here, and then by controlling the motor sequence, I can actually achieve four different kinds of actuations. Instead, I can achieve pure bending actuations, or so-called the mode 1 actuation, which is the twisting action, and the mode 2 actuation, which is we can consider it an adduction actuation. And then the last one is the mixed mode actuation, which is the mixture of all these three actuations. And then the second main part of the RTSPA is the so-called the SAM. So it is the design of the SAM here. So generally speaking, this is actually as most of them are made by 3D printed by TPU, but some parts are made by PLA for some special reasons. So you can see that here there are two main components here, which we can achieve the twisting and bending motion for this actuator. So the first one is this one, the base for the actuation unit. So you can see from the animation, the leg can be rotated, so it can facilitate the transformation of the actuator in this way. And the second one actually is the soft actuator base. You can see that in the design, I embed the whole air channel inside this base. So you can see that I supply the air here, and then through this channel, and then we can supply the compressed air to individual pillow like this in this configuration. And also there is one main advantage is that through this kind of the design, for example, if this pillow is broken, actually, I can just simply remove this one and then replace with a new one. So it is very convenient. It doesn't like the conventional actuator. If I break one unit and then you need to replace the whole actuator. So I think it is one of the greatest advantage of this actuator. Okay, and then after that, I have developed the mathematical model on calculating the transformation angle, which means that how many degrees of angle I can twist on the actuator based on the width of the pillow, because you can see that with different pillow width, actually there are different gaps between the width, and it may affect the transformation of the actuator. So actually, based on all these parameters, I have derived a very simple formula and then which can control the twisting angle of the actuator, and then based on different number of the width here. Okay, yeah, and then so here is the very this is the full picture of the demonstration of the actuator here. So you can see that here, you can see that I have different pillow width here from 5mm to 10mm. You can see that with a smaller pillow width and then the large gap between the pillow width. Okay, so and then there are two consequences here. So first one is that when there is an increase in the pillow width, actually you can see that the bending performance is better. Okay, and then but on the other hand, when there is an increase in the pillow width, actually the twisting performance is decreasing. The extent of twisting is decreasing. So you can see that. And then at this one, actually, when there's no gap between the actuator, actually it cannot perform any twisting motion at all. So you can see that maybe there is one consideration is that there is some compensation between the bending and twisting motion when we select different width of the actuation unit in here, and then to achieve different bending and twisting motions. Okay, and then after that, actually for the whole actuator, it is not, it is quite complicated to do the FEM analysis. So in here, I just choose to do the FEM analysis for the pillow and then to optimize my 3D printing parameters here. So you can see that in here, I set these three parameters. So the thickness of these three walls parameters. So you can see that in here, when I change T1 and T2, which is the thickness here, the top and the size, actually it has no consequence on the actuation performance of the actuator. However, when we change the T3, which is the thickness on this side, actually it affects the performance a lot. And then during the simulation, I set the unit can withstand maximum pressure of 0.5 megapascals. And then from the figure, you can see that the optimal thickness is about 0.9mm. However, for somehow of the safety operation to not to be easily fail, and also for more secure 3D printing quality, and last I choose 1.0mm as the final thickness for T3. And then for T1 and T2, I just choose the thickness which is larger than T3. So that's why I select 1.2mm as the thickness of T1 and T2. And then this is the whole design of the actuation unit. Okay, and then after that, after the assembly and of the whole actuator, I have done the characterization of the actuator. So the first one is the blocking force test here. So you can see that here is the blocking force test result. So it is quite obvious that there are two main outcomes here. So the first one is that when we increase the pillow width here, so for the banding, so in the banding, so it will increase the blocking force substantially. Okay, and then the second one is that when we fix the pillow width and then increase the transformation angle, and then the force just increasing gradually, but not a big jump. Okay, because that when there's a twisting, so the gap between the pillow is increasing. However, the center is start to align, start to misalign. And the misalignment is coming bigger and bigger when the angles is become larger and larger. So that's why the force is not increased so apparently. So there's just only a gradual increase in the force in here. So you can see here. So you see that for example, for this color, for 7.1mm. So when we increase the angle, so you can see that there is a gradual increase in the blocking force here. And then, yes, and then the last one I will show some application for this actuator. So the first one is the locomotion. So you can see that I have assembled a 4-leg robot, and then to demonstrate stability in locomotion. You can see that in here, it can perform a linear motion. So for example, in a horizontal one, and then you can transform and then to move in another direction. Or I can just transform the actuator in this way, and then it can rotate clockwise and then clockwise in this manner. Okay. And then you can see that in here, and one example, characteristic is that actually I can change the tip of the actuator and then to perform different kind of motion. So in here, you can see that for the locomotion, I use this shape as the tip and then to carry out the locomotion. And then in here, the second one is gripping. So in here, I use this shape as the tip and then to perform the gripping actions. So in here, Actually, for here, I developed a four-finger gripper, concentric gripper, and then to demonstrate the gripping actions. Actually, I discovered four different gripping modes in here. Okay, so the first one and the second one is the two-finger gripping and also the four-finger cage gripping, which is quite conventional here. So as shown in the video here. And then the third one is so-called enhanced opening four-finger gripping. So you can see that originally, if I arrange it this way, the opening is only 120 millimeters. However, after the transformation, I can increase the opening to 263 millimeters, which is a great increase in the opening. So it means that I can adapt to the objects, which is larger than the initial openings. As the pumpkin here, you can see that I can enlarge the opening and then to conform to the pumpkin and then to grab it up. And also for some kind of the fragile objects, just like the cupcake here, actually I can enhance the opening and then to approach the object. And then after that, I just decrease the opening and then to make sure that the gripper does not damage the cupcake or some kind of fragile object during the approaching motion. And then the fourth one is so-called the pseudo-parallel four-finger gripper. So in here, originally it is a concentric four-finger gripper. And then after transformation, you can see that it acts as if it were a four-finger parallel gripper. So you can see that for this one, originally you cannot grip the pack of ox in here in concentric mode. And then after transformation in the pseudo-parallel mode, I can successfully grip this kind of the rectangular backs of ox. And then the final demonstration is the object manipulation. So I use the same fingertip here for demonstration and use the same four-finger gripper here. So you can see that here I can do the two-finger object translation here, moving this way. And also I can also do the rotation, this kind of the parallel rotation here, by either two fingers or four fingers, or I can just mimic the human fingers on how to turn the cup like this. Yeah, either by two fingers or four fingers. Yeah. So this is the demonstration. This is the introduction of my first project. And then the second one, it comes to the second project. Actually, the second project is inspired by the octopus tentacles. So here is a very nice picture for the octopus here. So here is the explanation on how the octopus tentacle grip the object. Actually, it requires three stages. So the first one is called the reaching, means that the octopus tentacles try to reach the object. And then after that, when they reach the object, they will do the grasping actions. And then after the grasping, and then they will move the object back to the body, and we so-called the object transportation. So here is a more detailed demonstration on the grasping motion of the octopus tentacles. So first of all, the tentacle reach the objects, and then after reaching, it will grab the object here, and then after that, it will pull the object back to its body. Okay. So in here, actually, you can see that for different stages, it represents different kind of action. So for the first one, it is some kind of the bending propagation. And the second one is that we call the curve-like bending and then to grip the object. And then the third one, we can call the pseudo-joint formation as shown in the green circles here. And then to add like a robot arm and then to pull the object back to its body. Okay. Yeah. And in the current research, actually, there are a lot of research focusing on the bending propagation and also some kind of the fixed joints design. However, there is not so much research focused on the tunable pseudo-joints design. So that's why we are proposing the combination of the soft robotic arm design and also a sliding mechanism, and then to propose a tunable pseudo-joint formation. But in here, I will first introduce the design of the lightweight slider and for the pseudo-joint formations. So here is what we are going to demonstrate here. So here's the assembly of the actuator. And we use the TPU nylon bed and also for the sliding mechanism for the demonstration of the demonstration on how we form the pseudo joint. Yeah, so here is the video demonstration on how we do the pseudo joint here. So it is the parameters of the pseudo joint here. So in here you can see that the pressure applies here and then pulls the slider to different locations. So it means that actually when we supply different pressures, the slider will move to different locations and actually we can form the joint at different locations along this airbag. So this is the main idea of design of the sliding mechanisms. Okay, so in here, as I mentioned, the function of the sliding mechanism, there are two main functions. The first one is the formation of screw joint at different positions along the airbag. And also, the second function is for the air sealing. So we can see that here, let me pause a bit. Yeah, here. So you can see that when I pressurize here, actually there is no air leakage to this side. Okay, so the second function is quite important, and then to make sure that the slider can move smoothly on the airbag and then to form the screw joint at different locations. And then in designing these slider mechanisms, actually there is one main consideration is the weight. Okay, so as you can see that when the slider moving farther and farther away, and then the gravitation will do its part on the slider, and then it may hinder the motions of the slider. So actually, in here, in the design of the slider, actually we use the light materials. We mainly use the 3D printing technique, and then to do the slider and to try to increase the weight as much as possible, and then to not hinder the motion of the sliding mechanism. Yeah, and also we have also designed the rolling design model and also the forward force model for the slider, but I think I will skip this part for now. Okay, and then after that, after the assembly and design of the actuator of the sliding mechanisms, actually we have to do the characterization of the mechanisms. So the first one is the sliding force test, as shown here. So you can see that we have supplied two pressures here, P1 on the right side and P2 on the left side. So it means that for this actuator design, we can either supply pressure on one side. For example, we can supply pressure on P2, or we can supply pressure on both sides, which means that we can supply pressure at P1 and P2 at the same time. Okay, so here are some findings from this test. So the first one is that, so when we supply the pressure on a single side, the maximum pressure is about 13 kilopascal. And when we supply the pressure on the both sides, the sum of the pressures means that P1 plus P2 cannot exceed 17 kilopascal. Otherwise, we will damage the airbag. Okay, and then also here we have also do another experiment. You can see that there are three different lines here. I just take blue as an example. In here, we fix the pressure of P2 and then gradually increase P1, and then to see the sliding force on the actuator. So you can see that here, when we fix the P2 here, when the pressure is increased in the increasing phases, actually it is quite linear as shown here. Okay. However, when during the pressure decreasing phases, actually it is quite non-linear because of the hysteresis property of the TPU nylon bed. This is quite typical in soft robotics. Okay, and then another finding is that actually somehow we need some kind of the so-called activation pressure required to make the slider start moving. For example, take this one as example. Here, for example, when we set P2 as 3 kilopascal here, actually for P1 we need at least 6.5 kilopascal in order for this slider to move. So it means that actually, other than to overcome the pressures here, it seems that there are some kind of friction between the slider and the airbag, which hinders the motion of the whole sliding mechanisms. So it means that actually, in order to make the sliders move, we need to overcome the pressures P2 and the friction here. And here we can see that the friction is quite consistent here. So from experiment, we can also see that the friction between the slider and the bed is about 3.5 to 4 newtons here. And then we do another test and then to evaluate the friction force. And then the outcome is that the friction force is about 4.05 newtons, which is quite consistent to what we found in the previous experiment. Okay. And then actually at last, and then we also performed the reaching test here, and then to see the flow weight to the sliding speed of the sliding mechanisms, and the result is quite linear as shown here. Okay, yeah. So this is the second project I want to share with you, and then yeah, here is the third project, which is an ongoing project, and it is inspired by the seahorse tail. So as shown in the videos here, so you can see that usually the seahawk tail is usually curled when they are not doing anything, and they usually curl their tail to grip on the seaweed and then to resist the flow current to not be blown away by the flow current. Okay, somehow it is. And then also if they want to exert a larger gripping force, and then they can contract their muscle and then to curl the tail even more, and then to have a stronger gripping force on the seaweed. So based on this idea, we propose the 3D print soft recurve actuators, which have a downward actuation as shown in here. So when it is idle, it is a recurve shape. When we apply the negative pressure, and then we can straighten the actuator. And then when we apply the positive pressure, and then we can further roll the actuator and then to increase the gripping force of the actuator. Yeah, so here is the general design of the precurve actuator. So for this actuator, we use the golden spiral as the base curve for the actuator. And also, the second point is that you can see that for the width and height of the pillow, so-called pillow, so you can see that there is an increasing trend from here to here. Okay, and the trend actually it is based on the geometric sequence, based on these formulas here. Okay, and then after that, we try to do some preliminary tests using pneumatics first, and then to test the performance. So the first one, as shown before, so in here we just need to apply about negative 50 kilopascal, and then to straighten the actuator. And then when we want to further increase, and then, for example, we supply a pressure of 100 kPa here, and then we can achieve actually a very strong gripping force here. So and then after that, we also carry out a holding force test for the actuator to test the gripping the holding performance here. So actually, we used a 3mm inextensible cable here for the test. So in here you can see that when the actuator is idle, means that there is no pressure supply, it can have a holding force of about 23 newtons. And then after that, when we have a 100 kPa pressurized air supply, it can achieve an even higher gripping force of 79 newtons. And then, yeah, furthermore, we have a comparison of our actuators to the other proposed precurve actuators. So we can see that in our actuator, we have quite a few advantages over the past actuators. For example, we can have a pragmatic design, and we can have a very easy to use and very user-friendly 3D printing fabrication method here. And also, we can achieve both active and passive gripping at the same time for this actuator. And also for the gripping force, it is actually way larger than the previous proposed actuator in comparison. And then furthermore, actually, our goal for these actuators is that we want to use it as the anchoring in the underwater applications. So, for this application, the opening sequence is very important. So right now we are doing some kind of the FEM analysis, and then to consider these 4 parameters here, and then to see their effect on the opening sequence of the actuator, and then to optimize their motion. And then finally, here are some demonstration of the actuator in the underwater applications. You can see that we can anchor on a hull, and also we can grip water in underwater. And then and eventually it shows no leakage from the video, which is quite promising in this design. Yeah. So I think that's all I want to share with you today. Yeah. Thank you very much.
Okay. Oh, this is a really fantastic presentation. So we really like it. Yeah. Any question from audience now for Dr. Wan's research? Let's take a look now. Anybody ask a question? Please feel free to ask a question now, or if you like, you can answer our question after 2 presentation. Let me ask a question, Dr. Wang. It's really fantastic research. You have when you talk about your software. Let me ask you, so what's the torque control? So what kind of material? You're gonna use a three-dimension printer or how you made them?
Actually, for all for
Or
the
use the
first
first
one,
one, yeah, the
the first
flexible.
one actually
Yeah.
the flexible actually there are two materials. The flexible one I use the Ninja Flex as the TPU material, which has a hardness of 85A, and
Uh-huh.
the rigid part I use the PLA material.
Okay. When you twist or you bend, right? You twist and bend. So controlled by step motor or servo motor.
By this, I think it should be a very simple servo motor here.
Uh,
These two motors here.
oh, okay, I see. So when you needed to control our torque control, right? So to torque, you have you considered the torque control? Or
Right now in this model, actually, because I want to miniaturize the structure, for this motor, actually, I just use the angle control, position control
oh,
only.
okay, great. Great. Oh, yeah, that's really good. Great. So this is actually when you bend. So this is a material you three dimension, or you have to make yourself and put them, assembling them together.
Actually, they are consistent a lot of parts, and then I can assemble them together.
Okay.
Yeah. For
All
example,
right.
you can see here there are two bays here, and also, for example, 10 actuation units here, and also 10 bases here, and then assemble them together. So that's why so-called they are modular design.
Okay. Oh yeah, great. So can you see the screen? So somebody asked you a question in the slides page
Yeah.
two, second slides.
Let me take a look.
You have a many like a air pap. So second,
Second slide. Slide.
yeah, it should be, yeah. All right. Um, okay. How you prevent leakage? So for the,
I think the leakage, yeah, actually, during the design phases, the leakage problem is very severe. It's a very important question I need to solve. Okay, so I have done two things here. So for the leakage, actually mainly comes from here, the base. You can see that
Mhm.
actually I embed the air channel here. So actually, I just uh, prevent the leakage by fine-tuning the printing parameters. Okay,
Okay.
and then for this so-called the actuation unit here, so I've shown here I have done the FEM analysis here, and then I have set the maximum pressure I want the pillow to withstand, which is 0.5 megapascal here, and then from simulation it shows that the optimal thickness is 0.9 millimeter, but and then for safety reason I just increase a bit to 1.0 millimeters, and also for the stable usage, and also to secure the free printing qualities. Because actually, um, in you can see that actually I just increased 0.1 millimeters, right? But it affects the free printing qualities a lot. So it turns out that actually we need to fine tune the free printing parameters and then to achieve a good outcome and then to have low leakage.
Okay. Thank you. Thank you for your answer. Yeah. Thank you.